Hello, my name is Devin. I'm a graduate student in the Department of Physics and Astronomy. And today I have a show for you guys today about astronomy throughout the ages and sort of how the sky has been conceptualized by people. So I think that's all there really is to say with the introduction. This show was adapted from a show that's usually done at the William J. McKellen Planetarium at McMaster University. So I will stop the video so as not to distract everybody. So everyone should be able to see the title slide now. If anyone can't see the title slide, please say so in the chat and we can get started. Just a couple notes about chat etiquette before we get started. Please keep any questions in the Zoom chat, group chat window. If you type your questions there, they will be addressed at the end of the show. Also, please make sure your microphone is muted in the Zoom software or on your computer, on your microphone, or however you would like to mute your mic. Just please make sure it's muted. And I'm very happy to take any questions at the end. So, since long before the beginning of recorded history, people have been looking up at the sky. As humans, we can't help but look for patterns in the world around us. And virtually all cultures have looked up and they have noticed certain figures within the stars. One more thing, just a disclaimer. I am not myself a historian or expert on any culture, ancient, modern, foreign, or domestic. I simply have an interest in the historical and cultural roots of astronomy. In general, I think that we should all have an appreciation for history, because we can learn a lot about ourselves from studying the past. The history of astronomy is unique within historical topics because there have been some 40,000 generations of people that have lived on the Earth. And throughout all that history, each and every one of those 40,000 generations of people have looked up to the same sky. By learning about the differences in interpretations of the same phenomena, we can learn a lot about the perspectives of people living across great distances in space and time. Also, I would like to apologize in advance for what will doubtlessly be many horrible pronunciations of non-English words throughout this presentation. Now, in general, any pattern in the stars that you can make out with your eyes is called an asterism. But these official asterisms that have been recognized by the International Astronomical Union are the ones we call constellations. And we use these constellations as a convenient map of the night sky. And as you can see here, the Big Dipper, which you may recognize, is not actually a constellation in and of itself. Rather, it is a pattern of the 7 brightest stars in Ursa Major, which form an easily recognizable shape, or asterism. So that sort of illustrates the difference between the two terms. The earliest written record of the constellations can be found in a Greek poem called Phenomena, written by Aratus in 270 BCE. However, it's clear from the poem that the constellations were known well before it was written. And based on certain voids in the southernmost constellations and the precession of the sky, historians think the constellations were most likely first described by ancient Sumerians and Babylonians in around 2000 BCE. These constellations were later renamed and repurposed by the Greeks. Before 1919, a worldwide standard of constellations was not set, and different groups, scientific or not, had different asterisms which they would use to map the sky for scientific purposes or to point to in order to illustrate stories from their culture. But how long have people been studying the stars for? Let's stop for a moment and consider the earliest hunter-gatherers, who were likely nomads. With the lack of modern electricity, distractions, or even lighting, it was likely that at the end of each day, the people would gather together, likely sitting around a campfire. Perhaps they would be preparing an evening meal. Maybe they would share hunting stories or locations of the most plentiful berry patches. Eventually, these people are bound to look up and notice the patterns in the sky. And it's not unreasonable that people would then begin to make up stories about them, either in an attempt to explain the unknown or simply to teach morals to children. And it's probably safe to say that people have been watching the sky since the very dawn of humanity. But at what point did we go from simply telling stories of the sky to studying the cycles of the stars? When did we start using the sky to understand our place in the universe? How have we used the sky to improve our lives and civilizations? How did our ancestors see the world, and why did they see it the way they did? I hope that in some small way, we can answer some of those questions here today. The subject of the earliest recordings of the sky is the object of some contention. When we study history, we have to rely on written records, and these can be described as incomplete at their very best. Prehistory is even more difficult, the time before writing systems are found. Now, as far as we can tell, the earliest evidence of material depictions of the sky can be found in the Lascaux caves of southwest France. The caves were first discovered by exploring teenagers in 1940. Their dog had actually fallen into the caves, and they went down to rescue it. Inside, they found over 2,000 figures painted on the walls by early humans some 17,000 years ago. Nowadays, it's closed to the public in order to protect the paintings, but there are recreations of some of the caves nearby for the public to see. Some historians claim that some of these paintings may actually be the world's first known star charts. Many of the animalistic figures, like those seen here, may correspond to constellations or other prominent star configurations. Here is the so-called Birdman painting. It depicts a short-horned bull, a birdman, and a bird on a stick. And it has been argued by Michael Rappengleck of the University of Munich that the eye of each figure could correspond with the three stars, Vega, Altair, and Deneb, commonly referred to as the summer triangle. So here is that summer triangle, a bit more clearly in the sky. It straddles either side of the Milky Way. It runs through the center of the triangle like so. So we also note that Altair here is very close to the horizon. And if we were to watch the summer triangle throughout the night, it would not appear to be very prominent in the sky. Just like other star configurations, it rises, and at least part of it, in this case Altair, sets below the horizon. So it doesn't seem like it'd be especially notable for anyone who's looking up at the sky, but there is a problem with what we're doing. If these paintings were made 17,000 years ago, the sky will have been arranged slightly different. It's not enough to simply stand in the same location and look up at the sky, because while the star positions will more or less be the same, the orientation of the sky as a whole will be different due to a phenomenon known as precession. Now, in order to understand why the sky shifts, I need to quickly explain what exactly precession is. So if we think about a rotating top, we know that it's going to rotate about its central axis, but that central axis will also rotate in a circle as the top wobbles. This wobbling is what we call precession. We know that the Earth is rotating about its axis. That runs diagonally from Polaris at the celestial North Pole through the Earth to the celestial South Pole. But the moon and the sun tug on the Earth, and that causes it to wobble, so that the celestial North Pole of the Earth actually moves across the sky in a circle. Now, as a consequence of this, the North Star is going to change over a long period of time. Right now, the North Star is the star Polaris, the last star in the Little Dipper. But if we allow the Earth to precess, in 12,000 years, the North Star might be called Vega in Lyra. And another 8,000 years after that, the North Star will be Thuban in the constellation Draco. And after a full period of 26,000 years, it will return again to Polaris. So we would actually have to look at the sky as it appeared 17,000 years ago if we really wanted to see how the summer triangle appeared to those ancient ancestors. And when we do that, we see that the summer triangle no longer sets at any point in the year. No part of the summer triangle sets below the horizon. It's always visible. This type of star configuration is what we call a circumpolar configuration. And in all cultures that have written down their stories of the sky, circumpolar configurations of stars have played an important role in their stories or their culture or however it is that they conceived of the sky. So that leads a little bit of credence to the idea that the Birdman painting could correspond to the summer triangle. But there's one more piece of evidence I find a bit more compelling. This is a painting of an auroch seen in the Hall of Bowls of the Lascaux caves. Here we see the image of a long-horned auroch, whose horns are oriented in such a way that they could correspond to the horns of the constellation Taurus. And this is supported by the pattern of stars seen just over the bull's shoulders. This cluster of 6 stars could correspond to the star cluster known as the Pleiades, or the Seven Sisters, which is actually a cluster of 7 bright blue stars very close in the sky together. The fact that there are only 6 objects in the painting could simply be explained by poor vision. After all, the Pleiades has sometimes been used as a test for eyesight throughout history. People who are able to discern all 7 stars were deemed to have ideal to superior visual acuity, because most of us can really only discern 6. So now we've seen a little bit of evidence that prehistoric people not only recorded artistic depictions of the sky, but may also have taken star positions seriously enough to create primitive star charts. What is unclear, however, is if these people were able to utilize the information gleaned from their observations. Were prehistoric people able to notice the various cycles in the sky, such as the solstices? Was their knowledge precise enough to create a seasonal calendar, or was their knowledge simply limited to pattern recognition? This question is a difficult one to answer, because with very few exceptions, most of ancient knowledge was transferred by oral tradition. But one discovery can actually tell us a lot about the breadth of knowledge people had about the sky in Bronze Age Europe. This is the Nibra Sky Disk. It is a bronze disk about 30 centimeters in diameter, inlaid with golden symbols. These symbols are usually interpreted as the Pleiades star cluster, the sun, a crescent moon, a horizon arc, and a solar barge. It was found near Nibra in the Saxony-Anhalt region of Germany. Dated to 1600 BCE, it is the oldest concrete depiction of the cosmos in the world, and UNESCO's Memory of the World Register called it one of the most important archaeological finds of the 20th century. At this point, we've moved past the time of prehistory into the ancient period of history. And for the purposes of this presentation, ancient history will refer to the era after the advent of writing systems, around 3400 BCE up to about 700 BCE. So its depictions make it obvious that it has some astronomical significance. But the fact that it was found to be ritually buried, along with a small cache of precious weapons and tools, suggests that it likely has at least some religious significance. The sun ship on its bottom edge actually originates from ancient Egypt. It was said that the Egyptian god of the sun, Ra, would travel across the sky on a boat so he could be reborn at sunrise. This is remarkable because it signifies a link between the ancient Germanic tribes, who are often historically viewed unfairly as uncivilized barbarians. You can thank the Romans for that characterization, and the ancient Egyptians, who are well known as one of the most successful of ancient civilizations, success measured in how long they were around for. So let's consider the horizon arc on the disk. That's this arc here on the right-hand side. This inlay is the best indication we have of the astronomical sophistication of the people who used the disk in 1600 BCE. The arc on the disk sweeps through an angle of 82 degrees, which is a very significant angle in astronomy. If we look at the sun, when it's at its highest point in the sky, on the longest day of the year when the sun is at its highest point in the sky, that day is called the summer solstice. After which the days will begin to shorten throughout the year. Now, if we watch the sun throughout the day on the summer solstice, we could see that it sets in the horizon. Here in the northern hemisphere, it's going to set a bit closer towards the direction of north. Now, if we look at the sun on the shortest day of the year, when the sun is at its lowest point in the sky, we see that it sets at a point closer to the southern celestial pole. And the angle between those two points on the horizon is called the excuse me, the Solstice Arc, or the Horizon Arc. So this arc spans about 80 degrees, but the exact angle depends on your position on Earth. And as it turns out, in the Nibra region, where the disk was found, the Solstice Horizon Arc corresponds to 82 degrees, the exact angle of the Horizon Arc on the Nibra disk. So this precision indicates a significant level of sophistication in terms of the astronomical knowledge of the early Germanic people. And it's possible that the Nibra Sky Disk was used as a portable astronomical tool in order to predict the timing of the solstices. This is a very important date, especially in agriculture, because farmers would need to know the best time of year to plant or harvest their crops. So we've seen that the sky disk has religious symbolism paired with practical function centered on the horizon. The sky disk is an indication that European civilization as far back as 1600 BCE understood that the motions of the heavens contained patterns and cycles apart from the simple rotation of background stars. The ancient Europeans were not the only people to notice these patterns, though. Evidence that measurements of the sky were made could be found in the archaeology of civilizations all over the world, including ancient India, China, Mesoamerica, North Africa, and the Middle East. We recall that the Nibra Sky Disk included a depiction of an Egyptian sunship, and this is likely due to a cultural exchange with Egypt that has had a reverence for the sky throughout its history. So let's travel now to the latitude of Memphis in Egypt. During the time of the ancient Egyptians, Memphis was its capital city. It was the observation of cycles seen in the sky, primarily that of the rising and setting of the sun, that likely helped shape the theme of immortality and life after death, which runs through virtually all of Egyptian mythology. Like all cultures that studied astronomy, the Egyptians began by associating astronomical observations with their mythology, and these associations eventually led them to using astronomy to help in their everyday lives. The ancient Egyptians of 3000 BCE saw cycles in the sky, such as the motion of the sun and certain prominent stars, and they used those in their myths. One notable myth concerns the sun god, who is born as Horus as the sun rises in the morning. The blazing noonday sun represented Ra, the god of radiance, and the evening sun was Atum, the creator god. And at night, the sun god would die as it crossed the horizon, but would be again reborn as Osiris, god of death and rebirth, represented by the constellation we call Orion. Notice throughout this tale that significance has been placed on the horizon. It represented the birth and the death of the gods. This means that when observing the sky, it was likely that the attention of astronomical observers, astronomer priests, would be focused on these objects close to the horizon. Now, all of ancient Egyptian society was centered around one extremely important event, which occurred every year. This event was the flooding of the Nile. Each year, it would flood and then recede, after which the year's crops could be planted along its banks. As such, it was very important to be able to predict when the Nile would flood. Over many years, an event on the horizon was noticed to occur just before the flooding of the Nile. When the star Sirius appears on the horizon in the morning and is visible before sunrise, the Nile will soon flood. In fact, the first day this happens, that day is called the Heliacal rising of Sirius. And we can see here the glow on the horizon indicates the sun is almost directly on this solstice arc. It turns out that the Heliacal rising of Sirius is on almost the exact day as the summer solstice. And every year, it's just a few days before the flooding of the Nile River. Once they were sure of this pattern, they decided to structure their entire calendar around this notable event. The Egyptian year derived from this calendar consisted of 360 days, with 5 extra festival days at the end of the year for a total of 365 days. Compared to the modern calendar of 365 and a quarter days, this is remarkably accurate. Today, we use leap years to account for that extra quarter day. But the Egyptians did not, meaning that their calendar would cycle through the seasons over a period of 1,460 years. The calendar actually persisted long enough for the flooding of the Nile to cycle through their calendar for 2 whole periods, a true testament to the sophistication of ancient Egyptian observations. Now, there's one very important thing to note about these ancient civilizations that we have so far discussed. While some, like the Egyptians, did make sophisticated observations of the sky, and they noticed some of these cycles that we discussed, their ability to predict the motions of these objects, especially of the planets, were very limited. This is because ancient civilizations did not have the mathematical tools necessary to record and predict stellar motions, with one exception. The ancient Babylonians, who lived in what is now Iraq, practiced astronomy since its first dynasty in around 1830 BCE. Babylonians, like most civilizations, had mythologies about the stars. Like many others, they thought events in the heavens were messages to humans on Earth, and they made great pains to find what they called omens in the sky. An omen was a message to be given by the priests to Babylonian kings as a warning of what's to come. The priests, therefore, took great pains to make accurate and detailed accounts of the motions of heavenly bodies. Archaeologists have found a series of stone tablets called Enuma Anu Enlil, which contain detailed accounts of the motions of heavenly bodies. Any events which were considered outside the norm would be omens, and there were over 6,500 recorded in these tablets, thought to have been made between 1597 and 1157 BCE. The success of Babylonian astronomers is due in part to an important tool that contemporary civilizations lacked, and that is the math of a place number system and the abacus. They used a base 60 number system that first appeared in around 2000 BCE. This place value system is similar to our own, where the value of a digit is affected by its place in the number. This is contrasted by the Egyptians, which worked exclusively in whole number fractions. This allowed a degree of precision unattainable by contemporary civilizations. It's kind of like the ancient world's version of imperial versus metric. The idea that motions of celestial bodies could directly affect the lives of people on Earth, well, that should sound familiar to us. It is believed by many that the Babylonian civilization is the origin of what we now call astrology. The mathematical approach to this idea is what makes it distinct from the mythologies of contemporary civilizations. I think it's now about time we leave the ancient era and skip ahead to the era of classical antiquity in Europe. This is the era between 8th century BCE and 6th century CE. Greece was home to a series of very famous philosophers. The early Greek philosophers, called the pre-Socratics, collectively indicate a change in the way people in that part of the world thought about the natural world. The pre-Socratics, such as Zeno, Democritus, and Pythagoras, believed that the natural world was not the whim of the gods, but instead could be described by natural laws that humans could understand. One pre-Socratic of note is Pythagoras. We think that's this fellow sitting here in the lower left. Pythagoras was the leader of the cult of the Pythagoreans. He was also credited for the Pythagorean theorem. Yeah, he's that triangle guy. Anyway, he taught his followers that the world was perfectly rational and could be understood using numerical laws. Some accounts of his teachings claimed that the existence of irrational numbers, such as the square root of 2, was forbidden knowledge, only taught to high-ranking members of his cult. The idea that the world was rational and geometric would influence future philosophers like Socrates and his student Plato, who founded the first academy, which was called by that same name. And supposedly engraved above the academy entrance was the message, "Let no one enter here who is ignorant of geometry." Like the Pythagoreans, Plato and his student Aristotle believed the natural world to be a cosmos. This term implies a natural and understandable rational order. Now, when we watch the stars move across the sky, just as the Greeks did, and we watch them through the night, we see that all the stars in the sky move together. However, there are a few exceptions. It's obvious that two objects in the sky move independent of the background stars. These are the sun and the moon. However, there are 5 more objects visible to the eye that behave rather oddly. So if we watch carefully, we can see that some of the brightest stars, now called Mercury, Venus, Mars, Jupiter, and Saturn, they appear to move independently of background stars, apparently of their own volition. The Greeks referred to these stars as planetes, meaning wanderer. This was not a new observation. The motions of the planets, as we know them, were significant in the myths of many civilizations, including the Greeks. But the natural philosophers of Greece, they were thinking in new ways. They believed that the natural world could be understood at its most fundamental levels, and that the planetary motions were regular and predictable. Early Greek cosmologies were an attempt to explain not just the motion of the planets, but of the heavens and the earth. Greek philosophers took it as self-evident that the earth was stationary, and the planets, including the sun and moon, orbited around it. One argument made for this went something like this. If an archer were to fire an arrow straight up and the earth were rotating, then the arrow would fall back down and miss the archer. However, as we all know, this is a very dangerous practice. So in around 400 BCE, Plato challenged his contemporaries to prove that since the motions of the stars were normal and circular, the motions of the planets had to be normal and circular as well. We see in this argument that, or in this challenge, that Plato had certain preconceived notions of the nature of the cosmos, and he looked for evidence of those notions. This is contrasted to later philosophers like Aristotle, who attempted to develop theories of the cosmos based on observations first. At this point in time, philosophers were sort of arguing about what was the best practice. Oh, hold on, there we go. One contemporary of Plato, named Eudoxus of Cnidus, was a mathematician who developed this model in response to Plato's challenge. The circles in this animation represented the boundary of 2 spheres. The green circle represents the celestial sphere of the background stars, and the red represents a second sphere on which a planet could be found. The axis of rotation of the red circle is just off the axis of rotation of the green circle. The result is that any particular point can move in a figure-8 pattern, resulting in the retrograde motion of the planets that we observe as they do their little loop-de-loops in the sky. Now, this did a fair job of explaining the motions of planets, but it did very little to predict when each planet would undergo this motion. For these philosophers, the sun and moon were planets as well, so they had their own spheres. 7 plus the stars. Now, this idea did not satisfy Aristotle, who needed to know the physical causes of the celestial motions. It's likely that this attitude was passed on to one of his students. I'm sure you've heard of him. He was pretty great after all. He was Alexander the Great, who, after being tutored by Aristotle at a young age, went on to conquer much of the known world. In 323 BCE, the city of Babylon was conquered by the Greeks. The Babylonians were obsessed with mathematical precision in the astronomical observations, as we discussed. They thought that deviations from normal natural cycles in the heavens were omens, likely the root of astrology. The Greeks, comparatively new on the scene, at least with respect to the Babylonians' 1,500-year-old tradition at the time, believed that the universe was a cosmos of natural laws, which could be explained by geometry. And it is the merging of these two schools of thought which ultimately resulted in the modern quantitative scientific field of astronomy we know today. But it took a lot of effort to get there. With the adoption of a rigorous, practical, and quantitative approach to astronomy, Greek philosophers would make great strides in understanding the true nature of the world. Unfortunately, there are few surviving texts written during this time period called the Hellenistic era. Much of what we know about this time was deduced from later compiled works. The most famous example for astronomy is known as the Almagest of Ptolemy. Aristarchus devised a method of measuring the distance to the moon and the sun sometime between 310 and 230 BCE. Eratosthenes was able to measure the circumference of the Earth with remarkable accuracy for his time. His measurement was around 29,000 miles. The modern value, 25,000 miles. So remarkably close considering he was taking his measurements with tall sticks and some poor, I have to assume, the ancient version of a grad student who had to walk across the country placing those sticks. And it was Apollonius of Perga who in around 200 BCE first proposed the idea of epicycles in celestial motions. This idea was modified by Ptolemy around 100 CE to produce a complicated but effective geocentric model of the cosmos. In this model, the Earth and a mathematical equipoint are positioned on opposite sides of the center of a perfect circle called a deferent. A planet then travels along a second perfectly circular path around this deferent. This motion is called an epicycle. The retrograde motion of the planets is the apparent motion as they travel along these epicycles. This model was extremely popular as it effectively reproduced the motions of the planets while maintaining the Socratic notion of uniform circular motion. This geocentric model was so effective that it remained the most popular explanation of the cosmos for over 1,500 years throughout the Middle Ages and the European Renaissance. But before we can talk about later European astronomers, it's important that we take the time to recognize the work done in other parts of the world. As the age of classical antiquity and the Greek philosophers came to an end, a new age of philosophy would begin across the Mediterranean in the Middle East. The Islamic prophet Muhammad was born in 570 CE, and after his death in 632, his religion quickly spread across the Middle East. And in 762, the political and religious leaders of the Islamic states founded Baghdad, which would become the center of Islamic science and natural philosophy. Islamic scholars and inventors are responsible for many of the useful astronomical tools used by later European navigators, one of which is this armillary sphere. These spheres are originally credited as Hellenistic Greek devices used to model the geocentric solar system. However, much simpler versions could be found in ancient China, which were used to measure the heights of stars. It's unclear where they were first developed. This device may look a bit more familiar to you. It's called an astrolabe. It's another measuring device perfected by Islamic scholars, which was later used by European explorers. It can be used to measure the altitude of stars and planets by lining up one arm along the coordinate systems etched on its rim. This is actually a modern astrolabe, but medieval ones looked very similar. Islamic astronomy was motivated by two religious needs. The first being that mosques needed to know what time of day to hold their 5 requisite daily prayers. Prayers and mosques also need to be directed towards Mecca, the birthplace of their prophet. Islamic scholars had inherited their respect for accuracy from the post-Hellenistic Greek philosophers whose texts they studied, and they wanted to meet these needs as accurately as possible. To them, it was a way they could best serve their religion. So moving past the medieval era into the Renaissance, we start approaching our modern model of the solar system. As we saw in the Islamic era of science, the scholars learned by studying the writings of Ptolemy and the Hellenistic philosophers, and in Europe, this was much the same. For 1500 years, if you were an astronomer, you read Ptolemy's Almagest. There was just no way around it if you lived in the Western world. Because of this, the notion that the cosmos must be uniform and circular stuck in the side of science like a thorn that couldn't be removed, even as late as the 1540s, when Nicholas Copernicus published his book on the revolutions of the celestial spheres. This title reminds us that even until the 1500s, the notions that the planets and stars rest on solid, rotating crystal spheres remained from the works of Ptolemy and the other Greek philosophers. One of the nagging problems of the Ptolemaic model was that the moon should vary in size as it moves towards and away from the Earth. But the observed change in apparent size is much smaller than it should be. So Copernicus got rid of Ptolemy's equipoint, and he devised a new model of the solar system with the sun at the center. In this model, epicycles are not necessary. All the planets traveled in perfect circles around the sun, with the moon moving around the Earth. We now know, of course, that objects orbit in ellipses rather than circles. So you were so close, Copernicus, so close. The idea of perfectly circular motions persisted until the work of Tycho Brahe and his glorious mustache. This is actually Tycho pictured with his nose. At some point in his life, he lost his nose in a sword fight and then adopted a pet moose. He's quite an interesting historical figure. I think he also had most of the money in Denmark. Anyhow, more on him another time. He lived from 1546 to 1601, and he was obsessed with accuracy. And he has the well-earned reputation as the most accurate astronomer of the pre-industrial times. Tycho Brahe made several groundbreaking discoveries. The first was actually a brand new star, which appeared in Cassiopeia, bright enough to be seen during the day. Or so he thought. What he actually observed was a supernova. When we look at this spot in the sky with modern telescopes, we see this supernova remnant left behind. And the second discovery he made was the measurement of the distance between Earth and a comet. Remarkably, up until this point in history, people thought comets were aspects of terrestrial weather. They were not considered part of the heavens. Remember, in geometric models of the solar system, the planets existed on their own spheres, but according to Tycho Brahe's work, comets would actually move and crash through those spheres. That means they couldn't actually be there. These observations demonstrated that the heavens were not unchanging cycles, but dynamic systems that could change. This marked a shift in scholarly views towards the sky, which allowed for new models permitting true elliptical orbits. Another observation made possible by the detailed work of Tycho Brahe by later astronomer Johannes Kepler. Unfortunately, Tycho rejected the Copernican model of a heliocentric solar system. He instead favored the geocentric model with its perfect circles, and he attempted to produce his own Tychonic model of the cosmos. This conflict between geocentrism and heliocentrism was finally put to rest by the last astronomer I want to talk about from the Renaissance, and that's Galileo Galilei, an Italian astronomer who lived from 1564 to 1642. And he was one of the first astronomers to use a telescope to study the night sky, optics being a relatively new field at the time of the Renaissance. Galileo made many important observations of the sky. When he looked towards Jupiter, he saw its 4 largest moons, we now call the Galilean moons, in his honor. These are Io, Europa, Ganymede, and Callisto. These observations proved that the objects in the universe did not have to orbit around just the sun or just the Earth. Other moons besides our own existed, and they could orbit around other planets. The second and most controversial of Galileo's observations was the discovery of the phases of Venus, seen here. Venus and Mercury both exhibit phases, just like the moon, where only a portion of the planet's surface can be seen as it's illuminated by the sun. This is potentially the most important single observation in all astronomy to the Western tradition. Because with this observation, it can be proven mathematically that planets must be orbiting around the sun. They cannot be orbiting around the Earth, no matter how many circles you move them around on. In the preceding centuries, more and more discoveries would be made about the sky, but our model of the cosmos remained relatively unchanged compared to the massive swings seen during the Renaissance. And it wasn't until the work of Edwin Hubble that we begin to comprehend our place in the universe. Sorry about that. In 1922, Edwin Hubble discovered that there was what was once called the Great Nebula, and Andromeda was not actually a cloud of dust at all. It was situated right here in the constellation Andromeda. Not a nebula, it was actually millions of light years away, much farther away than any other star in the sky. Based on its distance, it could be nothing other than an entirely separate collection of stars apart from our own. A whole new galaxy, as it was termed. The Andromeda Galaxy, pictured here, otherwise called M31 in astronomical catalogs, is the closest galaxy to our own, the Milky Way. So, everyone's heard of the Hubble Space Telescope, I hope. It was named after Edwin. It is a giant telescope we put out in space in 1990 so that the clouds and atmosphere wouldn't get in the way of our pictures. And back in the day, astronomers decided that they would find the most boring patch of sky that they could. No stars, no nebulas, just a dark patch of sky, about the size of your pinky finger, held at arm's length, pinky fingernail, I should say. Just 1/10,000,000th of the whole area of the sky, and they gathered what tiny amounts of light they could from that little patch of sky over many days. And this is what they saw. This is the Hubble Ultra Deep Field. And within this image, there are over 10,000 sources of light. But each source is not a planet or a star, but an entire galaxy of stars, like our own Milky Way. Since these 10,000 galaxies are in 1/10,000,000th of the sky, that tells us that there are over 100 billion galaxies in the observable universe around us. Each, just like the Milky Way, contain over 100 billion stars. We also know from the recent Kepler mission that each one of these 100 billion stars has 1, 2, or even dozens of planets around them. And on some small fraction of these dozen, 100 billion worlds, there's at least the potential for a group of people sitting in their living room watching a long distance cast of someone talking about outer space, wondering what life might be like in that far off galaxy. That might be the Milky Way, who knows? Now, sometimes when we astronomers show people an image like this, it makes them feel small or unimportant. It's tempting to feel like humanity, no matter its progress, is ultimately insignificant in the grand universe we once thought ourselves to be at the center of. But I don't feel that way, because modern astronomers understand what old world astronomers and ancient philosophers didn't. Our world is not separate from the heavens above. We are not just studying some faraway pseudo-mystical objects when we look up at the sky. We are part of the heavens themselves, and the universe is within us. We are all made of the exact same material as the stars and the galaxies above. We are not mere humans studying the universe. We are in fact part of the universe that has learned how to study itself. And as thinking, rational beings, we are the only part of the universe that can. And that makes me feel pretty big. So I'd like to thank you all very much for listening. Have a wonderful rest of your day, and I'd be happy to take any questions you may have now. Feel free to type them into the chat. If you don't have any questions about the presentation, that's fine. You can ask any sort of space-related questions you want. We have a couple minutes before we're scheduled to end. How do you think knowing history impacts where we're going in the future? Well, history has lessons to learn. I think one of the biggest lessons we have here that I talked about in this presentation is, I guess, falling into dogmatic traps. The Greek philosophers, they were their early conflict was, do we make observations first, then build theory on said observations, or do we inherently understand what nature is like, and we should look for observations that help support that understanding? I think nowadays that's a trap that I imagine we see a lot of people fall into, especially in certain non-scientific topics. So being aware of how this can affect people's way of thinking, I think, is very important, because there was that preconceived notion that the world was perfect and rational, and circles are perfect objects. So therefore, nature had to be structured in these circles. And this didn't leave scientific dogma for 1,500 years, or longer than that after its inception. People, who knows where society would be if it only took people, say, 100 years to get out of that preconceived notion, to actually look for evidence of that first. So that really stalled us for an incredible length of time. So I think that's one very important lesson. We learn from history so we can avoid the mistakes of the past. Are there any other questions? I hope that answered your question. Okay, if there are no more questions, I'd like to thank you all again for coming. Feel free, if you enjoyed this, come back tomorrow, same time, where you're going to hear a talk by, oh, sorry, one more question. Go ahead. How much of the sky are we actually observing today in terms of large objects that may be potentially dangerous? Very little, very little. So yeah, we still get what we call near misses, where an asteroid or comet or some sort of large piece of space debris has come dangerously close to the planet, and we don't even know until it's closer to us than the moon. We aren't tracking all the large dangerous objects out there because no one wants to pay the taxes to pay for it, or no one wants to otherwise assign the funding to pay people to guard us for this stuff, or guard us against these objects. So yeah, that's just, we have some people who are dedicated to this problem, how to find and redirect asteroids, but there's very little funding available. So that's just something we just have to hope nothing terrible happens in the foreseeable future. That's all we're doing right now. Yeah. Any other questions? Okay, thank you all very much. Tomorrow, Paula Bosca is going to be talking about the NEUDOSE satellite project, specifically about the high altitude balloon launch we're going to be taking part in, called SBX. So please come by tomorrow and sit with us for an hour or so. It'll be in a format similar to this. I don't know if it'll be the same Zoom link or another one, but there's, I imagine there's going to be updates in the event page. So thank you all very much for coming, and have a wonderful night.